Today we have the pleasure of having a panel session, and I'll be your moderator. So I'm Brian, and I'll have the speakers introduce themselves to make sure that we all know their backgrounds and their context of how they're answering.
So I'm Santosh Vempala. I'm at Georgia Tech. I study algorithms and I'm interested in the complexity of computational problems. And for the past decade, intensively, I want to understand the brain rigorously.
Hi, I'm Eran Malach. I'm a research fellow at Harvard Computer Institute, working on ML theory of deep learning, and kind of more recently on starting to think of like theory of language models.
I'm Jacob Andreas. I'm at MIT. I'm going to be giving a talk tomorrow and thinking about natural language processing.
And Tomaso, Poggio, and I like compositionality, and I'm interested in optimization and whether it works and when it works for compositional functions.
Great. So I think for the format, we're going to have audience also ask questions, but also in the meantime, while audiences are preparing their questions, I'll ask maybe a first question, which how have research priorities shifted now that we have these kind of huge models, but even larger data sets for these models? Like, has the paradigm changed for how you think about your own work?
Jacob?
Yeah, so I mean, I think maybe the biggest thing that's changed for me is that, even when I was in grad school not so long ago, it felt like a lot of the questions about sort of how do you build computational models of human language processing and human language acquisition, and how do you build models that generalize in human-like ways from sort of human-sized data sets, felt like they were sort of on the critical path to also accomplishing all of our engineering goals and building language technologies that were actually useful for doing things out in the world. And it does feel like those things have diverged a little bit in the sense that, there's still a big role for language to play, or for computation rather to play, for example, in our understanding of human language use and language processing and language acquisition. But I feel like now progress on those things is not necessarily progress towards, the GPT-5 or whatever the next big LM is going to be.
Yeah, for me, I think I thought that until transformers came around, the architecture to be considered was basically convolutional deep networks. And now there are a number of other architectures that are intelligent to some degree. So there is a real zoo of intelligent architectures. And the question comes, what are the fundamental principles that make them work so well? It's not just a single architecture. And there may be many more that I'm pretty sure that people have not yet thought about.
Great. So then, do you think transformers is the kind of end of the architecture search, or do you think there's something that we will, or the kind of like an intermediate process?
If it's the end of the road.
Yeah. Very
surprised. Also because they have clearly serious limitations. Just look at, the last, I don't know if it's a paper, but achievement of DeepMind with a silver medal at the Olympic, Math Olympics, yes. That's a combination of transformer and other things, among them reinforcement learning. I think transformer by themselves, that's my guess, are not enough to get, the best possible intelligence.
I think for me, like, things are kind of changing all the time, and the paradigms are changing all the time. As Tommy mentioned, like a few years back, convolutional networks was batch norm and dropout. This is what everyone did, and the network were like highly overparameterized. And then there's like a lot of learning theory focused on explaining why batch norm is so important, or why dropout is so important, or why convnets or overparameterized networks are super important. And now we're training on basically infinite data. We're not doing batch norm. We're not doing dropout, and the architecture is completely different. And this is within, a few years. So I think definitely we should not like stick to the architecture or the paradigm that is working right now and say this is how things should work, because in like just a few years everything is changing, and we want to maybe try to understand or explain kind of the fundamental principles and not necessarily what we kind of got working right now with the current hardware and technology.
Yes.
You still want me to answer the
Oh,
first
okay.
question? Yeah,
Go on.
sure. Yeah. So yeah, I've always thought that it's just a matter of time before computers are going to be just as smart as humans, or smarter. They're machines, after all, and so is the brain. But it was very hard to convince a lot of people. And now with transformers, at least now you can say, hey, look, it's doing what you thought was impossible. So that's one great aspect in life in general. Concretely, I love the problems that come up. Why is next token prediction doing very well at that? So giving you so much ability, so much power. I think it's a question I don't understand. And
Can I just one more thought responding to all those things, and also to your initial question. I feel like maybe even the biggest thing that's changed, at least from the sort of part of the field that I sit in, is that it's gone from being an engineering discipline to something that feels more like a scientific discipline. That it used to be, you would come up with some clever new model for task X, and in writing down that model, you would also have a sort of pretty precise description of the kinds of things that it was going to be able to do, the kinds of things it wasn't going to be able to do, the kinds of ways in which it was going to generalize or not generalize. And now we have these sort of weird computational artifacts that do all these things that we didn't expect them to be able to do, and are much more in the mode of just sort of trying to describe and explain rather than design from first principles what's going on. And I feel like actually a lot of the way we even just like train people to do research in the field hasn't caught up to that.
Okay, so then related to that, I guess, like in terms of things that haven't caught up, like what common assumption in deep learning do you think needs to be abandoned, whether it be in theory or just deep learning in general? I think everyone has to answer this question, so no one can avoid it.
Do you have candidates in mind?
Well, I mean, there's examples like, dropout was something that was very popular, and then it kind of left.
Drop out.
Yeah. So there's a history of things that didn't stand the test of time, I would say. But do you have your own kind of personal belief that's something popular now that, might not stand in a few years from now? Think, Eran?
I would say I would hope that we would go beyond backpropagation gradient descent to maybe this is an extreme view, but it seems that with all the research that people in the field are doing, it's all very focused on training neural networks with gradient descent, and we have no other algorithm for at least for these kind of problems. And the brain was mentioned in previous talks, and I think it's maybe pretty clear that the brain is not doing backpropagation gradient descent. So it seems that there's a better algorithm out there, and we just sort of need to find it. So maybe this is kind of the big thing that maybe not in a few years, but looking into the future, maybe this is something that would change.
Talk was actually using a model that was learning not with backprop and also learning things in not an IID way. So do you have any kind of beliefs about that?
Yeah, I mean, at least in the model and the way we can understand things right now, there's a very helpful teacher. I mean, the environment is helping you, like the human experience. So in terms of what might change and what to be dropped, I guess the lesson is that really don't be too attached to the current model.
There are, when I spoke about briefly about the conceptual approach of machine learning, I said it's to find a parametric approximation to the unknown function, and deep networks are such an approximation. But there are other approaches non-parametric. For instance, nearest neighbor, no parameters. You decide to look for the key. So, and there are other ways, so-called Watson something estimator. It's similar. So one could try to explore this non-parametric way to learn, but that's going beyond, outside the normal traditional deep learning. It's more like trying other directions that may be quite good.
Jacob, do you have a...
Yeah, I think that largely been said already that, basically don't get too attached to any specific architecture that we're using right now, because, historically, at least the kinds of shifts in choice of architecture that have happened in the field have really been driven more by sort of computational constraints rather than, this is actually like somehow this parameterization is a better fit to all of the tasks that we care about than that parameterization. And I would expect that to continue to be true.
Cool. So since this is a theory workshop, and I think a lot of the talks have been on like aspects of verbalization and overfitting, just for each speaker, like, what do they think about since models are training on so much more data now and their parameters are very large, like, do you think it's an issue of overfitting or underfitting? Because the CEO of Anthropic recently said the training cost is going to go from 10 billion to 100 billion in the next 3 or 4 years. So I'm wondering if you feel that the problem is overfitting or underfitting, which is a bigger problem in the space right now. Tommy, do you want?
Well, I think overfitting has been exaggerated in the sense that you can have more parameters than data and effectively not overfit because you have constraints like regularization. It's not the number of parameters necessarily that gives you, control capacity in a system, but is regularization and other properties of the network. So you can overfit and generalize. That's fine. In the old version of VC theory, this was not possible because essentially the hypothesis space was fixed and the main results were for increasing number of data. But you can formulate equivalent results in a framework in which the hypothesis space is not fixed and still get generalization even if you overfit. If you fit the data and you have more parameters than data.
Yeah, I think maybe you're related to this. We're now, these big language models are pretty much trained without repeating data. So it's kind of like in the online setting, which is, again, like maybe a few years back, we would worry about generalization and overfitting. Now you're training in the online setting. In some sense, there's no worry you only care about optimization because generalization is in some sense for free, right? Because you're doing this online learning procedure. Each example is new. If the loss is dropping, this is all you care about, right? So maybe there's out of distribution generalization or generalization to new domains that you don't see during training. These are still open, but kind of the classical notion of train test difference is no longer a problem. Which is maybe nice. We got rid of this generalization problem. We're only left with how can we optimize these things? Yes.
Yeah, I agree with the comments about generalization, or at least so it seems. Though I still don't know the proofs that more parameters doesn't seem to hurt you. Generalization for a specific task or distribution, but I find particularly puzzling how we seem to learn higher level things. I mean, you play, tic-tac-toe, you learn how to play it, and then you play Connect 4 or something, then you play something more complicated. And by the time you learn the next game, you've learned something, even for a game you've never seen before. You learned how to learn to play. And I'd love to see this maybe it's already doing it. Maybe somehow Next Token is capturing all this. but how? Yeah. So
Actually, that's a good question, because I think in the first lecture when Tommy presented this notion of compositionality, do you believe that the models can learn compositionality the way Tommy kind of specified it as, like, building concepts that are just stacked on top of each other rather than individual concepts one at a time?
I mean, certainly for efficiency, it appears that that's a crucial element to keep both the sparsity and the compositionality. And given that all empirical training seems to be quite efficient, I would guess that there is some level of this, either because of regularization or other things that's being done. Whether that generalizes across distributions and across tasks, or how it does that?
Well, you can imagine you have various constituent functions, various modules that are common among different tasks. And so if you learn those, it's like having maybe a large dictionary of skills, or the constituent functions.
Right, which you might not have learned explicitly.
Yes.
Point, right? Some of them at least. Yeah.
Some of them may learn explicitly, others may learn during learning more complex compositions. But if they remain available, it's all pretty vague.
But yeah, just going back to the underfitting or overfitting discussion, I feel like, in some ways, actually, the problem is not that so much as that we don't actually know how to specify the distribution that we're trying to fit, after all. I mean, like, going back to what Eran was saying in the talk earlier today, we're really good at building models of the entire internet. The problem is that the language model that you actually want to hand to somebody to use is not a model of the entire internet. It, has a consistent personality. It, like, speaks in, it doesn't necessarily, like, generate incorrect facts, or, say too much or say too little. It's not sensitive to cues that the user, might put into the input, like misspellings or things that would generally be correlated with, then bad behavior from whatever prediction was downstream of that. And I think the problem that we have right now is that, that system, that interaction that we want to build, you don't get from training on the entire internet, because the internet doesn't look like that. You don't really get it from the various kinds of clever fine-tuning techniques that we have right now. And so the problem is that we just don't actually know how to specify what it is that the target distribution we're trying to hit.
Well, that's great. So then I have a follow-up question to that. So I know all of you, or some of you, have done work in this direction, which is, why do models hallucinate? Like, why do they hallucinate? Why do they generate things that are not even in the training set?
I'm happy to start, because the only theoretical paper I've written on language models is about hallucination. The title of the paper is "Calibrated Language Models Must Hallucinate," and this is with Adam Kalai, who came up with the idea and wrote the proof. But basically, the one thing that has been shown is that if you just do loss minimization in, say, some of the standard loss measures, the models tend to be calibrated to the input, so in various senses, to the input distribution. And once it's calibrated, you can show extremely simple notions of general notions of what are facts and non-facts, that the hallucination rate is essentially lower bounded by the fraction of unseen data. And so that's just a theorem. It doesn't matter whether it's independent of architecture. Any statistical language model which hasn't seen some fraction of data is going to hallucinate at roughly that rate. So it seems inevitable. And indeed, I think it's a very important problem about how to I guess, provide feedback so that we move away from this to more reliable outputs. Yeah.
Yeah, I mean, something that is sort of a trivial follow-on from that, right, is that if you have a data set in which nobody ever says, I don't know, then the model's never going to learn to say, I don't know. And, always if you're asked a question that you sort of don't know the answer to, the loss minimizing response is to place a sort of uniform distribution or, whatever, the right posterior over things of the right type, rather than just to say, I don't know. And you can't have simultaneously a model that, sort of assigns probability proportional to the right answers, which is something that we do want for a lot of applications, and also have a model that communicates to a user, hey, I have uncertainty, I happen to sample this token right now, but if you call me again, I'll give you a different output instead. And, I think one of the really interesting, again, sort of empirical questions there is, there's this behavioral characterization of hallucination, right? Does the model sort of say, I don't know, or does it give you the right answer, or does it make something up? It seems totally plausible that even in the setting where you have a sort of calibrated language model that's giving you this distribution over answers, there's some internal representational correlate of knowing the answer or not knowing the answer. And I think figuring out, if we had a better handle on how knowledge, certainty, whatever got represented internal to these models, then it would be much easier to take a model that is a good sort of calibrated model of the distribution and just turn it into something that says, I don't know, and in the right circumstances are back again.
Could it also be that since the language models are trained with cross entropy, that it finds like that is a mean fitting objective, and so then it just like upweights parts of the distribution that could have been lower in the actual distribution of language?
So the point is that even if you have a perfect model, let's say you've learned the distribution exactly, the training distribution, but you haven't seen some fraction of the data, you're going to hallucinate. So it's independent of the mechanism, not only the model, but also the mechanism by which you acquired your model. Yeah. One thing I wanted to say I wish at this point I was a language model, I could remember. Oh, yes. What I would love for GPT to do is to output the probability, that what it thinks is the probability of what it just generated. I think that should be a law. Like, if you're going to tell me this is the completion or this is the answer, just give me your real confidence, like what the probability of your model is, which obviously they must have because they sampled from it. And then that way I can make a decision whether I want to trust it or not. Maybe my bar is 0.99 and somebody else's bar is 0.5, or depending on the task. But they don't do it right now. I ask it, what's the probability in your conference? And it gives me a different number each time because it's using just another generation to do that.
Well, but what do you actually want there? It's certainly not the probability of the string, right? Because, for any answer to a question, there's a million ways of expressing it. You have uncertainty over how much detail the user wanted. You have uncertainty over.
If I say the sun rises in the blank,
yeah,
it will say east and probably give me 99.7.
Yeah.
Right?
Well, no, because it could have also said morning. It could have said, some very precise angle. It could have, I think the hard thing is exactly the figuring out how do you translate the entropy of this distribution over strings into somehow the entropy over concepts.
Okay. Jacob had a salmon burger had a blank for lunch.
Yeah. And
then it says, sorry, I gave it away. Salmon burger, right? What's the probability? Is it true?
What? No.
But you guys, it could have been, right? Yeah, so.
Maybe this is just from my perspective, but it also often feels like, especially recently in ML theory, that there's this sort of loop where something works and then not necessarily your papers, but a lot of people will come out with papers explaining why that thing works. But often it feels like that's not really the right direction things should be going, and theory should be, informing the applied sciences. So my question is, what are the best pathways for ML theory to inform, applied ML today?
I agree. And it's often a problem. And I think it's maybe some of it is a consequence, like the kind of explosion in technology and the value of just putting a ton of engineers and kind of pushing the state of the art. And you don't invest so much money in like learning theory researchers to kind of catch up with this. So it's the kind of like thousands of engineers that are kind of moving forward, and then like much less people that are trying to do theory. And it's definitely, you want to be able to explain what's happening right now. And ideally, when kind of I agree that kind of the ideal role of theory would be to kind of point out, what is the right thing to do in the future, and not just explain what we already know. This is, of course, much harder. I think, like in some aspects, like there are theoretical works that are doing this in kind of like certain areas, but it's I think right now mostly due to kind of I like the analogy of like the time before Maxwell is like there's kind of this explosion in technology that is just happening, and I think that over time the theory will just catch up.
Yeah, let me take a controversial view and attack computer scientists. You guys, I think in the theory of machine learning until 15 years ago, in the time of kernel machines and so on, the overall picture from the theory point of view was pretty clear. And so what theoreticians had to do was, details, fixing things, finding useless bounds, things like that. And now we are in a new era. It's more like natural science. It's like physics. There is transformer that spits out stuff, and we don't know why it works. It's not a question of proving a formally correct theorem. Is what is the basic principle? Is like, is it fusion of helium atoms that power that? Like, it's this kind of questions, fundamental question. Forget the formal details. I think it's a different, in a sense, machine learning today is become a natural phenomenon. Your computer that this was, by the way, the title of my talk was computable intelligence or mathematics, because this mathematics and machine learning actually does useful things. It's a natural phenomenon that we have somehow to explain. And that's a different framework. A priority is not having formally correct bounds, but is more finding the principle, the basic principle that makes these things work. So, sorry, did I offend anybody? I don't think anybody here is actually guilty, but maybe some people in the community have been, emphasizing, let's say, this kind of old mode where...
Maybe let me try to respond. There's like scientific theory, which is like, you can think of like physics as a scientific theory of nature.
Science,
yes.
Right?
And
things
then there's like...
in nature.
And there's mathematical theory, which is maybe like the kind of thing
nature or not.
You're trying to criticize. And these are like similar but maybe different things. And I think like a mathematical theory is often like a part of a scientific theory, and not always that all of the theory has to be mathematical, but there's definitely value in doing mathematical theory as part of like developing a scientific theory. And I think that the power of mathematical theory, even in like today's paradigm of learning, is that it can tell you things about experiments that you cannot run. Like if I ask you, what would happen if I gave you like, exponential compute and the size of the problem, will you be able to solve it or not? This is not something you can do. You cannot run this experiment, but you can only do mathematical theory. And asking the question, these questions of lower bounds, what are the problems that you can absolutely not solve, even if I gave you like, an extreme amount of resources? This is not something you can ever answer with an experiment. And I think there's value in these kind of theoretical statements. This is a problem that you cannot solve, no matter how much money you put into this or how many GPUs you buy. And I think that
some of the more powerful results in physics are this no-go theorem, showing that some model, some kind of type of model can never explain, for instance, quantum mechanics or the some of the puzzles in.
So I guess to help the computer sciences out a little bit. So neuroscientists arguably, at least as a field, has contributed many things to neural networks. But recently, there hasn't been as much transfer, I would say. Maybe the most recent one being Fukushima and the comment being inspired by that. Why is that, and what can you do about that?
Well, Santosh may be a counterexample where you have.
How does he inspire you, Santosh? Like,
I mean, the brain is the most solid example we have of artificial general intelligence. Of general intelligence. You see, got me. But so yeah, I mean, you can't. It's the lack of a theory is absolutely mind-boggling. But just to related, but going back to the question, I think explaining phenomena has always been part of science. Certainly, yes, the phenomena, the hot phenomena in machine learning are changing rapidly. That's a bit of an issue. But nevertheless, the lots that we'd still like to explain, right? We don't understand, and we'd like to explain. But I guess there are also, as all three of them have pointed out, questions that have emerged that just we didn't see before, and that is fantastic. That now that we have this possibility of AGI, one I like in particular, and I feel is very important, is safety, which can take many aspects, but. For example, we talk about bias in all kinds of AI, machine learning systems, certainly in generative models. And there are all these fixes, right? There are people try to fix it because of whatever reason, and it works and it does breaks. It works and it breaks. But what would we like AI to be? We'd like it to be, sure, unbiased, like we want ourselves to be unbiased. We'd like it to be ethical. Why not? We'd like it to be altruistic. We'd like it to be kind. All these things, right? So you can go back and ask, well, what I'd like to ask is, how do I get AI to do this without doing a smart fixes? Keep fixing it. That seems like what is it called when you keep whack-a-mole? No, it's not going to happen. We didn't do the whack-a-mole with humans, right? Somehow, humanity, for the most part, decided that these are things we're going to have as a society, and it's working. So, well, evolution doesn't, in this, the culture and ethics only happened in the last, 100,000 years or so after language. At which point the brain has hardly changed, whereas with AI, what can we do, or what is missing to make it have this naturally? Right? Is it because we're putting all our resources into one unit, so it doesn't care about sharing anything? Is it because the objective is just loss and not something else, or is there some other more complicated, thing that we could incorporate into AI that will make it safe in all these senses?
I think on that note, there's this kind of space now going on. It's kind of an emergent field of mechanistic interpretability, which from my point of view has been very observational and very empirical. How does theory help with the notion of interpretability of models that are already trained that exist today?
So the example of this phenomenon that's most on my mind right now is, there's a lot of talk about sort of world models and language models and to what extent can they simulate things. And, we have all these nice results from sort of formal language theory and circuit complexity that talk about, for a transformer-shaped thing, what are the classes of problems that you can solve, and what are the classes of problems that you can't solve. And one of them is just simulating general, unrolling of automata. And so if you have a language model that looks like it's doing something, if you have finite depth and finite precision and all the usual caveats. So if you have a model that looks like it's doing sort of state tracking with an arbitrarily complex state for an arbitrary number of time steps, it can't actually be doing that because we know, we have these sort of negative results that under standard assumptions. There is no such circuit that solves that problem. And so I think to the extent that you're then engaged in the business of observational, sort of theory building, hypothesis formulation about what's going on inside these models, knowing at least the sort of theoretical impossibility results constrains the set of hypotheses that you need to entertain about how a model is solving a problem, and maybe tells you something about what kinds of shortcut solutions to look for instead.
So that sounds like you can, given the architecture, figure out the bound of what it could possibly do to simulate something. And if it's doing something that seems more advanced than that, then it's probably doing it in an incorrect way.
Yeah. Cool. And I think that's at least one category, or, and then in the opposite direction, right, where we know, okay, here's a great algorithm for solving this particular task. Our first guess at how a model is doing solving some problem might be to look for that algorithm specifically. And I think there's been lots of recent examples of this in the context of things like in-context learning and yeah.
Yeah, I think for theory, I mean, there's a lot of like theory works on kind of simple, maybe synthetic tasks that we kind of understand well. And these tasks often there's not like a lot of ways to solve them. There's like multiple possible like algorithms or solution that you can implement, and then you just need to kind of check and see what is the algorithm that the model is actually learning. And we often see that if you kind of look at this correctly and you probe the model correctly, it did learn one of the kind of possible algorithms that you had in mind. So definitely starting from a problem that you know how to solve, and then like looking at the model and seeing how it solves the problems is definitely like the right way to do it.
It's like a well-defined toy environment where you know what the ground truth is and solving from that.
I was wondering, what are your thoughts on how neural networks and machine learning in general maybe have changed our view of the world, or what have we learned about the world? And I don't mean in a narrow case where we learned the structure of a protein and now we discover new proteins and we make stuff and we understand the world better, but rather as maybe a shift of perspectives on how we think about the world. Because main thing I've studied is machine learning, and now I look at everything as distributions that we learn and representations and what is the minimal representation, stuff like that. So I was wondering whether you have thoughts on this.
I've always found that science is kind of a social phenomenon, and for instance, what it means to understand a phenomenon varies not only across different fields of science, but also across time. There was a time when I arrived at MIT in the 1980s, that it was a very successful time for molecular biologists. They were pretty arrogant in general. And, for them at the time, finding a gene involved in a disease was understanding the whole problem of that disease. Of course, we know now that, finding a gene is just a step. Then you have to understand how the proteins that the gene encode for interact with the disease, it's complicated, right? But at the time, finding a gene was understanding. And the scientist who got a Nobel Prize for discovering, I forgot whether neutrons or neutrinos, said the rest is chemistry, right? So I wonder whether, machine learning will change what we mean for understanding a problem. So for instance, let me take example from what I did in the past. Back again in the 80s, we developed with David Marr an algorithm to solve stereopsis. You take two images, you can compute the distance and the depth from the disparity from the two images. Now, you don't need to understand the disparities involved, where it comes from. You could, in principle, train a machine learning model with a lot of stereo pairs and the ground truth, and the system will learn stereo. Will that be understanding stereo? You don't... I don't think so, but from a certain practical point of view, it is, right? If you understand how machine learning works, you may understand, in principle, you know how to solve a lot of other problems without really understanding them. I think that's dangerous, but that's one way. You ask how machine learning can change our, science, and in a sense, that's one way. So I think it's even more important to try to understand how machine learning works, right? Really.
I completely agree. I mean, at least this is one bad effect of machine learning. People feel like scientists cannot afford not to do it. And it gives you these seemingly impossible problems, solutions to some level of solution. And unfortunately, then you move on to it's not satisfactory like it used to be.
For instance, this is another good example, which is really a big accomplishment, is AlphaFold. So you can infer the structure of the 3D structure of proteins from the sequence of amino acid. And that's the first program that should get a Nobel Prize. But it's a big problem, and it's a problem that, from a computational point of view, probably should be NP complete. You don't solve really the folding problem. You don't really understand in the program how proteins fold. You understand through data. You may understand it's too much word. You predict through data how the final 3D structure is going to be. That's, but it's a big thing, and.
I feel more concretely even in natural language processing. I mean, it's amazing what computers can do for translation now. It's better than basically.
And translation.
Translation,
yeah,
right?
Absolutely, yeah.
But still, which is great for users and for people who are not in the field. But I feel like it must be a hole for people who are in the field. Right? Previously, whatever fragment of language you understood, you really understood. And then there were things you didn't understand. Now it's all big, sorry.
Oh, I mean, just going back to what Tommy was saying before, I think there's an interesting analogy between, on one hand, the sort of process of scientific modeling and scientific model building and theory building, and on the other hand, the problem that these big unsupervised neural sequence models have to solve, right? And I think the sort of biggest or most surprising thing in all of this for me is that, within some relatively large family of like pretty simple, pretty unstructured neural net type architectures, if you train on enough data, you get good at all these problems that seem to require understanding a lot about the latent structure of the world, and that in some cases, people only seem to be able to do because we've like really been hardwired to do them, like language learning, or that require going off and getting a PhD or spending several lifetimes accumulating scientific knowledge, things like figuring out how building models of the process by which proteins fold. And I think it's still then an open question whether these neural sequence models are solving these problems by just noticing a bunch of sort of shallow surface heuristics, or whether there are actually things about the natural world that are getting learned inside these models that somehow aren't known to us, that we somehow need to, sort of build tools to pull out. And that feels like one of the big sort of exciting, important challenges, is just that we have these really good predictive models that in some ways allow us to, we can run experiments on that we wouldn't be able to run in the real world. And, for all of the problems that we care about, the work now is figuring out, are those problems getting solved by these models? One, in a way that actually reflects the true data generating process in the real world, and two, in a way that allows us to derive some kind of scientific insight.
I was still thinking to the problem of hallucinations in generative models, and I had a question regarding this. So, do you believe that one methodology that we can exploit to, let's say, train these models in the regions of their representation where they are not trained with actual data, could be training these models with their own generated samples? And in general, what do you think about this technique, like training the models on their own generated samples? Do you think that this can be helpful in the future of deep learning?
In some sense, this is done. With definitely in the fine tuning or RLHF phase, you are like generating from the model and like based on like different ways to like rank the generations. You can kind of fine tune the generations of the model. And presumably now more and more models are trained from like synthetic data, which is basically generations of the model. So I think this is becoming more and more popular to do. I guess maybe the question is like, can you kind of bootstrap this way, get a better model by training on your own generation? And there's some recent works that give different answers in this. Maybe other people know better, but I think it's currently not very clear how much better you can get by training on your own generated data, unless you have some kind of sophisticated mechanism to kind of throw out the garbage, basically.
Yeah, there is a recent paper showing garbage in, garbage out, and
Going back to deep learning, which was the model of this panel, this data augmentation, right, by data perturbation was a very successful technique. I believe it's still quite successful. One way to, for example, do better at adversarial examples and so on. So it has its certainly merits using data generated by the model for various, for improving. Whether it will get rid of hallucinations, that's completely unclear. For that, we might need what Eran mentioned about human feedback or other kinds of feedback.
And isn't your theory like theoretical researchers? So maybe that's not your strongest side, but as someone that doing more empirical work on deep learning, I'm really thinking about whether do you know maybe Francois Chollet ARC challenge or ArcAGI? Some of you, I see you're nodding out of that. Okay, so he basically he presented a benchmark that shows a generalization problem with current ML architectures, let's say. And he basically, if you have any notion of what's the next type of model or any idea, any intuition that is not necessarily based on deep learning, if you have something to it, okay? And if you know the ARC challenge, maybe you can reference that. That would be great.
We will split the $1 million now.
Yeah.
I mean, do people know this? I don't know. Maybe.
If you don't mind explaining.
So it's. Do you want to explain it?
I don't know. I'm really stressed. I think it would be better if you would.
It's basically these kind of visual puzzles. You get like 2 or 3 examples with kind of simple rules that humans kind of figure out very easily, but apparently it's hard for basically any AI models. Currently, they're very far from human level performance, and there's a prize of I think $1 million or something.
It's not $1 million. Yeah, $1 million. Yeah, prize. So basically, humans get 85% on this, and currently machine learning, I think, gets 40, and that's by the last month. But I think it really references the problem of generalization, with the LLMs and current machine learning paradigms.
Yeah, so I think
if not, it's okay. You can move to the next question.
I mean, of course, I don't know if I have a solution. Otherwise, I would go for the $1 million. But I think one of the approaches that I saw that people try for this problem, I think is interesting, is basically try to generate a lot of programs from the language model and basically kind of choose the best ones and maybe iterate, which is also something that is becoming more useful for code and math, which is, I think, the interesting idea here, maybe from a theory perspective, is this challenge and maybe actually a lot of problems, we have very few examples of input and output, and you need to figure out the rule. And if our only paradigm for doing this right now in machine learning is train a neural network with gradient descent, it's a terrible idea when you have very few examples, because you'll immediately overfit and nothing would be learned. But another approach is actually maybe much more data efficient, is really to kind of try out a bunch of different hypotheses and choose the one that kind of works best. And this is actually a very simple, efficient thing to do. There's a kind of classical learning theory results that the number of examples you need for this is kind of logarithmic in the number of things that you're going to try. So this is very data efficient. And in some sense, this is kind of the one of the solutions that people are trying is just try out a large number of things and choose the ones that work best. Is actually a pretty good algorithm if you have kind of like a heuristic of what to try.
Yeah, this will be also non-parametric approach in a sense.
Hello. So, do you think the scientific community is doing enough to supervise the application of these technologies such that they do more benefit than harm, and also maybe to counter potential exploitations such as those deep fakes? So if yes, what are these attempts? And if no, what can be done?
I mean, it's a very important question. Obviously, we don't know the answer, but it requires, it's the type of service that I think none of us can escape now. We all have to spend some time trying to formulate what would be a satisfactory approach to even formulating so it'll include some regulations, it'll include some cultural development. It's such a new age, right, with all this possibility of, so obviously we don't know the answer. Some transparency, some honesty. People have tried, for example, you might have seen this pledge several months ago trying to say, stop the use of development of generative AI for a certain number of year or something, and that didn't go anywhere in spite of a lot of famous. But we don't want to wait for something really disastrous to happen. There's enough bad things already going on.
Yeah, and I think just adding to that, there are things that the scientific community can do alone, but at the end of the day, the decision about, how to regulate these technologies and what constraints to put on them is not not a decision for the research community to make on its own. And probably the most valuable thing we can be doing right now is just engaging with the public, with policymakers, making sure that people really kind of understand what's possible, what's not possible with current technologies, and contributing to the public making of these kinds of decisions rather than trying to make them ourselves.
Yeah, I don't know if I have anything interesting to say about regulations, but I think what I find interesting is that we kind of still don't know if we're kind of a few years away from something that is like superhuman and it really is like intelligent in the way that we mean intelligent, or that it's just kind of like a smart Google that can, retrieve things from the data set, maybe do some manipulations, definitely very useful, but not intelligent in the way that we humans think of intelligence. And I think maybe this is kind of like the fundamental question. Because, definitely you can do harm with language models the same way you can do harm with Google search, right? But this is not the question. The question is like, is this thing going to develop like in kind of, real intelligence that can do like actual harm just from like the fact that it developed intelligence in itself? And I think like, I don't know what the answer is.
The answer is yes. Of course, there will be intelligence that's supreme. The question is just when and what are we going to do about it?
Well, but there's also lots of harms that you have to start thinking about well before that point.
Exactly.
Yeah.
Like it's already, we should be.
Yeah.
Kind of following on that, I guess you could think of humans as also large models, but multimodal. And then following on from that, you can kind of think of, for example, creativity or like discovery, like the hallucinations. But it's kind of, from our view, it's justified because we have all of the information from all the other modalities. So like, do you think there's a difference between, I guess, humans based on kind of your subjective experiences and a very big multimodal model?
The title of the book will be "I Am My Language Model." But
it won't be a language model because you can't just use language. It's not sufficient. You need to
language model in the general sense that it's a generative model. But no, sorry, that was just a tongue-in-cheek answer. Yes, there are some high-level similarities between creativity and hallucination, and I don't know the answer to your question, but something related that I feel like maybe we can try to answer is something I've forgotten.
It seemed to me like neural networks, like the one you use now, they're very passive observers of the world most of the time. They like kind of simulate our perception. They take data, they have some input, which is a concept, but they're not acting like we do. And like there are some machine learning that acts like AlphaGo and stuff like this, but they're using like other kind of frameworks, which is I don't know, maybe less successful or at least less stable, like reinforcement learning, which is like a little behind. Or do you think we need like a new theoretical framework for kind of acting and strategizing in the world, or do you think reinforcement learning is enough with some perception that we have already quite figured out, or at least quite advanced, or do you think there is no problem? I don't know.
Sorry, I'm still answering the previous question now, but here is the thing. We haven't seen, as far as I know, a new insight from a generative model. We've seen amazing stuff, but I haven't seen a truly fundamental new explanation.
But we have seen hallucinations.
Yes, absolutely. So whether those hallucinations are the ones that lead to creativity that gives you a new insight. So so you could summarize it by saying what's known is known and what's not known is not known. I mean, they're doing very well so is that a drawback or a fundamental limitation of language models not being able to come up with a new insight, or is it just that we're not there yet in terms of capacity and training? I don't know. But so far there hasn't been like, oh my God, I now understand how this thing works, which we didn't know before. That hasn't happened yet. Yes, you can solve an IMO problem, but so can 10 other people. So I don't want to distract away from the next question, which was about something very interesting. Do you need to embody to be intelligent? Yeah.
I'm not sure. This was maybe more about like active interactions with the environment. So the recent IMO silver medal was exactly this, right? Like we're doing some sort of some variant of like search and reinforcement learning for like generating like math solutions to problems, and it seemed to like give good results. So I would say that definitely this is something that is becoming more dominant in the field, and like definitely for like these kind of solving math problems or coding is definitely very useful.
So yeah, this is just going back to the what is theory useful for. I know Tommy mentioned maybe this is his bias as a background with a physics background, but there's more. There are more sciences than just the natural sciences, right? You have the engineering sciences. Like if you think back to when we built bridges with new materials, I read this recently. Apparently, they first built a huge chain with steel to figure out what the sag would be without knowing the equation for a catenary. So I like to I'd like to think about these new demonstrations as these are how you this is how you would do it, but the demonstration usually comes first, and then you go back and try to figure out what are the conditions under which this is possible. So I think there's another role for theory in terms of thinking of this as an engineering science rather than a natural science. So
it's kind of a follow-up in the question of embodiment. So is it a shortcut to go straight to use language? Because at the end, language is the structure that humans found to describe the environment. Shouldn't we expect that if we want agents that develop their own intelligence, they should either be able to interact with the environment to extract concepts from the world, or let them like have some input modalities and they should recover on their own some computations and language that will make sense to compress the information they are receiving. Like a fly has the brain that's uses different types of coding. So should we keep pushing for like intelligence language models when this language will never have access to the environment that's created those embeddings?
I mean, so there's two, one question is, do you need embodiment to sort of learn things about how the physical world works, right? Are there things about, that we learn from having actions, having access to vision, hearing sounds that we never describe in text, or that, we don't sort of encode in text to the precision that you would need to like build really detailed models of the real world. That seems like almost certainly to be true, right? There's all kinds of really complicated, you can't, like, among the many things that language models can't do right now is solve really complicated, like, motion planning problems. And there's a lot about just like, what it takes to walk, or what it takes to, grasp a glass without dropping it, that we never talk about, and that we really only learn by being in the world. And if we want models that can do those things, certainly you need access to all those other sensory modalities. There's a separate question then of whether you need interaction or whether you can learn these things purely observationally. And I think one of the big surprises, again, with what shows up in a sort of sufficiently large natural data set is how much about the kind of causal structure of the world you can get in purely observational terms, right? And all these things, these sort of like Pearlian, well, you can't really tell what the causal relationship is from this pair of variables observationally. But then in the real world, the data says, well, I'm the doctor and I'm giving the patient this treatment and this is what the outcome occurred. And there's a lot of just like people talking about causality and people describing running experiments in the real world. And, if enough people describe their experiments to you, it's as though you've done those yourselves. Whether we could learn more efficiently by actually being able to do the interactions, almost certainly. But there it seems less clear that there's, it's not the sort of thing that could at least naively be solved by scale.
All right, if there are no more questions, so let's thank the wonderful panel.